really exciting and very interesting event for organizing this. And so what I will talk about today, my talk will be split in roughly 2 parts, trying to focus the first part a bit more on the question of quantum observers, or which quantum information we'll refer more to as agents, quantum agents. And the second part on questions related to causality, very much in the spirit of the very nice talk that Nelson just gave us on the idea of so-called indefinite causality, or these sort of events and localization. So that would be the second part of the talk, and we will look at some relations between them. So this is based on 2 joint works. The first part is based on joint work together with Misha Woods, which is on this idea of quantum agents, which is studied in these so-called Wigner's friend scenarios, and we're very happy that just a few days ago it was accepted in PRX, so hopefully should appear soon. And the second part of the talk is based on joint work together with Lingqing Chen, Yuhang Ye, and Renato Renner, 2 of them who are in the audience as well, which I'm very happy about. And yes, so that I start by thanking my very nice collaborators, and yes, so then I will be mainly focusing on these 2 works during the talk. Okay, so throughout this conference we've heard different notions of causality and events, and clearly we recognize that especially across quantum theory and general relativity, we have rather different notions of causality and events. Right? And on one hand, in quantum theory, especially from the more information theoretic side, one can define causality and events more in operational terms, right? And for instance, you often see these kind of circuit diagrams, and these give you a notion of causal influence to how information flows through them. So here M1 is before M2 in some sense. In this, we look at these operations and the way they're connected. And often this is inferred through some notion of agents who can come and intervene on some systems here and see that this changes some observable predictions on other systems in this kind of circuit diagram. On the other hand, in general relativity, we've seen that events are tied to the idea of space and time, and where we refer to the light cone structure of the space-time to order our events and talk about causal structure. So I would argue that it's quite important to reconcile these notions, at least to some extent. Of course, they're very different, but and one to sort of continue the dialogue between the communities, but the other is to talk about, say, even physical experiments, in some sense, are situations where you embed these kind of circuits and operational stuff into some notion of space-time. And so they have to play together in some way. And moreover, when talking about questions at the quantum gravity interface, naturally, we've seen in the discussion so far that both sort of concepts pop up, and we want to understand how they relate. But this is naturally quite challenging because they're quite different a priori. And of course, we've also seen that in quantum gravity context, we cannot assume some classical background space-time which gives you a fixed light cone structure to order your causal, to get your causal order. And moreover, typically in quantum information frameworks, these agents who perform interventions are treated as classical and external entities. And to have a more complete picture, one would require to consider whether we can also treat the agents as part of these circuits and as quantum systems in their own right. So this raises questions on extending quantum theory both to observers and agents and to space-time itself. And this should add the disclaimer, there's a very cartoon type diagram, but basically the field of Wigner's friend scenarios looks at extending quantum theory to agents themselves, for instance, where we can have a superposition of an agent observing an outcome A is 0 or an outcome A is 1. And as we've seen in the previous talk, in scenarios where both quantum and gravity play together, one might naturally consider sort of superpositions of gravitating masses, and which can lead to some kind of superposition of quantumness in space-time itself, right? And of course here, as I said, this is just an illustrative diagram. There can be, of course, many different models of quantum space-time or quantum gravity, where one is not necessarily looking at these kind of linearized superpositions as pictured here, but this is just an illustration. And these are, of course, often studied independently, but interestingly, in both fields, recent results highlight that we need to rethink the notion of events and causality. And moreover, one can argue, and indeed arguments have been made, that more like these, in each of these scenarios, one needs to consider some more relational as well as operational approaches, right? And in the part one of the talk, I will focus on the first, on Wigner's friend scenarios. And the second part of the talk, I'll focus on the idea of events and their localization and causality, but without assuming a classical spacetime a priori. And in part three, which will be more brief, I'll try to talk about maybe some connections and open questions. Okay, so just to recap, so in this very influential paper from 1961, Wigner proposed this interesting thought experiment where imagine that you have some agent, Alice. She has a quantum system S in her lab, and Alice tries to measure the system, right? And she sees some outcome A. Now, we imagine a second observer, Wigner, for whom the entire lab of Alice, which here I denote by the system S, together with this A denotes the rest of Alice's lab except the system. Okay, so together S and A constitute Alice's lab, on which Wigner can now measure, and he can obtain some outcome W, right? And here, naturally, for Wigner, he's treating Alice as a quantum system on which he can act in the same footing as Alice treats this system S. And in recent times, there's been a lot of interesting work considering extending this set of Wigner's friend scenarios to more agents and more complex situations to provide more interesting arguments. So in particular there, the important thing is that in these extended Wigner's friend scenarios, one models other agents' labs, like one agent can model the lab of another agent as a unitarily evolving closed quantum system. So for instance, Wigner could model Alice's lab in the previous example as really a closed quantum system, which we might describe as evolving unitarily. And moreover, and this is an important aspect, not just that, now Wigner can in fact perform operations on the entire lab of this agent Alice, and which can really, for instance, measure in different complementary bases and so on, right? And just to illustrate, in typical quantum frameworks, we are usually treating agents as somehow effectively classical, which is distinct from the quantum systems that they act on. But in these sort of extended Wigner's friend scenarios, one can have an agent treating another agent in the same footing as the quantum systems. And sort of these kind of divides are usually called sort of Heisenberg cuts. In a more philosophical sense, we will soon see what role they play in our framework. And indeed, there have been interesting no-go theorems that have suggested that once we move from the standard to these Wigner's friend type scenarios, one encounters potentially radical challenges for logical reasoning of the agents, or even for having some absoluteness of the observed events that they share, and for causality itself. And of course, these are some of the first works that propose these no-go theorems, and there have been since then many more such no-go theorems in different contexts. Okay, so this naturally raises a question of is it even possible to, like even at a basic step, is it even possible to do science in a Wigner's friend scenario, right? Like if two agents measure some, or if a set of agents obtain some measurement outcomes, and these are not absolute, right? So we were talking about measured results, then how can they sort of reconcile their observations, and how can they sort of reason in a consistent way, and how can we make scientific predictions and agree upon them if events are not absolute, right? And secondly, so as we know, all this weirdness can happen in these Wigner's friend scenarios, but clearly we seem to experience some notion of absolute events, right? So if we perform the Bell experiment in the lab of one colleague or a lab of a different colleague, if it's kind of set up in the right way, they would end up agreeing on the results of that. So how can we explain the apparent emergence of objective classical outcomes in existing quantum experiments? And in this work, we will answer both these questions through a quantum circuit framework, and we basically generalize the quantum circuit framework to these extended Wigner's friend scenarios. And a key ingredient there is giving a formalization of this idea of Heisenberg cuts. Okay? And so this will inherently be a slightly like a relational version of the quantum circuit framework, as we will see. And I want to add a disclaimer here that in this whole literature on Wigner's friend, especially these no-go theorems and as well as our works, you don't have to think of these agents as conscious human beings. In fact, what makes it interesting is that in principle, a quantum computer that's complex enough to measure a system, store the measurement outcome in a quantum memory, and perform some basic reasoning steps could act as an agent in these scenarios. Right? So indeed, it's not so clear where this kind of cut should be drawn a priori. Okay, so now I'll give the idea of this quantum circuit framework by just trying to put the existing Wigner's friend scenario as a circuit diagram. So say that our initial system S is prepared in some superposition state, then Alice performs a measurement on that system, and let's say Alice just measures it in the 0-1 basis, and then Wigner comes along and measures Alice's entire lab. If you remember, this was the system S, and A denotes the rest of the lab, but you can, for this purpose, think of A as just the memory in which Alice stores the outcome of her measurement. Okay? And then Wigner comes along and measures in this basis. So just to explain this a little bit, so here when I say 0, 0, being the state of S and A, you should think of this as the state of Alice's lab when she sees the outcome 0. And similarly for 1. Right? So you can, even if it's a complex system, you can kind of, what we care about are these sort of effective qubit degrees of freedom. And now Wigner is essentially doing a Bell basis sort of measurement. Of course, this is not a complete basis, but given this initial state, this will be enough to consider. Okay? So now the important question is, how do we model this measurement? Like on the one hand, if you take Wigner's perspective, you could say that Alice is a closed quantum system, must evolve unitarily according to the unitary postulate. And so Wigner might evolve the state to this pure state. And this, as you can see, as we've defined here, is the state that's called fail, so that with it deterministically. On the other hand, Alice would say that, well, I performed the measurement in the 0-1 basis. I applied a projection postulate. And according to that view, the final state of the lab would either be 0, 0 or 1, 1, or maybe some mixture where I say that, okay, the measurement was performed, and there was a classical outcome, but I don't know what it was, right? And clearly, these two situations, if you compute the probability of Wigner's outcome under these two situations, they're different, right? And so it highlights that the ambiguity in how to apply the postulates of quantum theory in these scenarios surprisingly has empirical consequences, right? It's not clear what prediction we should make for Wigner. And I will go on to label these two cases as XA is 0 and XA is 1. This is just telling us how we are modeling the measurement of Alice. And this shows that indeed the probabilities, the predictions we make depend on these choices, right? And just we notice that if we kind of ignore these settings here, I will call these XA to be the settings. If we ignore these here, then it looks like we get some kind of contradiction, because here the probability is 0, and here the probability of Wigner saying OK is non-zero, right? So it sort of highlights that somehow this would become important to keep track of. So the way we now model this in our framework is to make explicit these settings, XA, which model this choice of, so we'll indeed think of them as modeling Heisenberg cuts, but more formally, they're kind of telling you how you're describing a measurement, as a purely quantum evolution, or as something that produces classical records, which is through the projection postulate. And that's the 0 and 1 here. And so by default, the measurement is now modeled here as a unitary. And then we have what we call the setting condition projectors. And they're rather intuitive. When the setting is 0, this is just the identity. So the whole evolution is the unitary. And when the setting is 1, this is just performing, like this is applying the projectors in the basis of the measurement, right? And now you can actually identify a non-trivial classical record. So importantly, when the setting is 0, we don't identify a classical record. But in the second case, indeed, even to talk about A is 0, A is 1, we are talking about which projectors identify them. And yes, so as I said, this kind of formalizes the idea of the Heisenberg cut. And I won't go into the details, but in the paper, we show that this idea can be generalized to any Wigner's friend scenario with any number of agents. We can kind of take it and turn it into this, what we call the augmented circuit, that gives the Heisenberg cut for each of the measurements. Okay. So now I will try to highlight how we can use this to resolve the kind of interesting paradoxes that have been proposed in the literature. And indeed, the first one, where it comes from the Frauchiger and Renner paper, where they were the first to consider the question of agents' reasoning in these Wigner's friend scenarios. And here I'm just presenting a very simplified version of that protocol, which was, I believe, comes from some of the talks of Matthew Pusey and Louis Massanes, which is an entanglement-based version, while the original protocol was a more sophisticated prepare and measure one. But all the arguments we'll give will also apply there, but I'm happy to take questions if there are on that aspect. So essentially what's happening here is we kind of have two wings of the Wigner's friend kind of experiment, but with an entangled state shared between Alice and Bob. And this entangled state happens to be exactly what's called a Hardy state, which actually goes back to the Lucien Hardy's proof of Bell non-locality without the inequalities. And in any case, you can see that here the Alice and Bob measure their part of the system, bipartite system, in the computational basis, while the Ursula and Wigner measure the labs of Alice and Bob respectively in the OK-fail basis. So we'll call Ursula and Wigner the super agents and Alice and Bob the agents, right? And the no-go argument in the paper was, of course, this is again a simplified version. They formulate the assumptions under which you get this claim. But the main idea is that if we now apply quantum theory to these agents, Alice and Bob themselves, and then consider how we can reason about the measurement outcomes, and indeed this is something we naturally do in the physical world, right? Like in a Bell experiment, Alice can try to say, I've seen the outcome A is 0, what would Bob see if he measured in the same basis, for example? So if you do this kind of reasoning, they find a paradox in this scenario. And just to give an outline of the reasoning, the idea is to post-select on the outcome where Ursula and Wigner get OK, and this has a non-zero probability, so this will succeed. And then one can show, and this indeed is in this entanglement version very similar in spirit to the Hardy kind of argument, that if you start with this OK, then Ursula can reason about what Bob would have seen for measuring in this basis, which would be B is 1. And then Bob can reason that if he sees B is 1, then Alice must definitely say A is equal to 1. And then Alice can reason about Wigner. So they sort of all reason about compatible pairs of agents. And they would conclude that Wigner obtains fail. So you see this, you kind of obtain a paradox with this line of reasoning. And now if we look at this in our framework, we would need to condition on how the measurements are modeled, especially for the agents, Alice and Bob. So this is just a comparison to show that now within our framework, this paradox gets fully resolved because now the statements can no longer be combined through any axiom of classical logic to lead to a contradiction because they are a condition on the choices of Heisenberg cuts, and these are clearly different for each of the statements. And I won't go into the detail here, it's an informal statement of the theorem, but we can really prove this for any Wigner's friend scenario, any number of agents. One can prove a sort of completeness and consistency result, which is in sort of the spirit that this construction will guarantee consistency. And moreover, there's a sort of causality condition relative to these Heisenberg cuts, which says that basically say if I'm making a prediction for Wigner's outcome, this cannot depend on the Heisenberg cut of an agent who's outside the past light cone of Wigner. Right? And this follows from the fact that we have a circuit framework. And the nice thing is that there's an objective part that agents can agree on, and there's a subjective part. The objective part is the augmented circuit, right? And this has a well-defined operational causal structure the agents can agree on. The subjective part is that they can choose different Heisenberg cuts. And I will go a bit more quickly through this part. This is just to highlight that in light of this, there's really no contradiction between the previous works, Frauchiger and Renner, and what we are saying, because this is really, once we have this sort of Heisenberg cuts, one way to see the result is that they're really talking about two different versions of quantum theory. So indeed, if one goes for a version of quantum theory where we don't talk about Heisenberg cuts, and you might say, okay, this is what we use in the real world, then this this leads to contradictions in the scenario they described. But what we show is that in Wigner's friend scenario is well motivated to indeed consider a cut-dependent version, because we do choose different Heisenberg cuts and they do matter. And once we choose that, we can prove consistency for all Wigner's friend scenarios. Okay, and now to this quickly the second question. Can I ask how much time I have left? That's good. Thank you very much. Okay, so I'll go a bit quicker through this part. This was the question of now when we have this sort of more relational kind of framework where things can depend on Heisenberg cuts and measurement events are not absolute, how do we kind of recover the perceived objectivity of events? And for this, we introduce a new concept called what we call the non-superagent structure. It's a bit of a mouthful, but it's just trying to capture under which situation does Wigner not act as a superagent to Alice, right? Because indeed, we don't see superagents in the real world, at least as far as we've been able to explore experimentally. So the idea is that imagine I have this sort of structure where Wigner is acting on the lab of Alice. The question is to ask, can I describe this scenario in an operationally equivalent way through a scenario where Wigner's operation only acts on the system and not the memory or the rest of the lab of Alice? Okay? And if the answer to this is yes, then we would say that Wigner is not acting as a superagent to Alice, right? Because there's some part of Alice's lab that kind of can carry away the classical record, as we will see. But if this is not the case, that Wigner is really performing a genuine joint operation on the whole, it would mean that Wigner is really acting on the entire lab. This would mean that Wigner is a superagent to Alice, and we would say that this pair does not belong to the non-superagent structure. And using this, we can define a precise distinction between standard quantum experiments and Wigner's friend type experiments. And standard ones are precisely those for which all pairs of agents belong to the non-superagent structure. So no one is a superagent to anyone else. And then we can show that in these standard experiments, everything becomes independent of the Heisenberg cuts. The augmented circuit reduces the standard quantum circuit framework, so everything is consistent. And one can give it a nice physical interpretation in terms of somehow persistence of classical records. Because indeed, if you, in these standard experiments, there's always some system that carries away this information, which I could later measure to extract the outcome of Alice. So I can define the Alice outcome and Wigner outcome jointly. Okay, so I think I'll start moving ahead a bit. There are a few additional results connecting it to like other no-go theorems, but I'm happy to discuss it later. And also this idea of Wigner bubbles. And maybe this is also clear, but just a quick take-home messages of in this framework, we can, because we account for the Heisenberg cuts, can give a resolution to these Wigner's friend paradoxes. And what I find interesting is that now we can try to extend questions on standard quantum information theory to Wigner's friend scenarios, including causality questions. Okay, so now for the second part, maybe I can motivate what's the goal for the second part, which can seem a bit ambitious. So here what we are looking for is to find a general definition of events and their localization, which in particular can recover the sort of quantum and relativistic notions that we know in these fields. But also we want to do so without a priori assuming a background spacetime, right? So we want it to be applicable to these kind of quantum gravity scenarios like the examples that Nelson presented in his talk. And we still want some way of talking about causality, because indeed in those examples there's some notion of causality, at least in this context of indefinite causal order or circuits. And moreover, I want to stress that it's not that we want to give one definition that should be the definition, but the idea is to more try to extract some common features across different definitions and without assuming a particular theory or model, so that this can help us to promote dialogue between the communities to try to identify what choices are we making for those different features. And at least some key questions that such a proposal should address is, okay, now how can we define localization? Localization relative to what if there's no background spacetime? And moreover, again, similar in spirit to the question we asked in the first part, how does this explain sort of the more objective predictions in known experiments? And by this I mean the fact that known experiments typically happen in a classical spacetime, so how do we recover those predictions? Yes, sorry. So the proposal is to define events relative to a structure that we call lab, or a generalized lab. And the main ingredients of this lab are first is a choice of a reference degree of freedom, right? So you can think of this as some physical degree of freedom, and importantly, we should be able to measure this, and we define this measurement through some set of measurement operators that come with some labels which you can think of as possible measurement outcomes. So for instance, if it's a clock, your measurement outcomes would be labeling the different time readings. Then you have a target degree of freedom, which is the system that we want to study. And we consider some set of operations, right, that act on the reference and target. So ideally, these are some conditioned operations which say that looking at the reference being in some subspace, I apply some operation on the target. And in this sense, we will refer to any such operation as an event, right? Okay. And importantly, this encodes a number of choices. It encodes a choice of what is the level of detail at which I'm describing these reference and target systems, right? Because as we even saw in the first part, we could describe all of Alice's lab in a very coarse-grained level as 0 and 1, even though this might be a rather complex system. And this can, of course, happen in many different physical experiments, so it's important to fix a level of detail at which we are talking about events. A more colloquial example, perfect, thank you. A more colloquial example would be whether we consider this conference a single event or a succession of many talks, many events would depend on in what level of detail we're talking about the conference. Moreover, it's a choice of what is the reference and what's the target, and a choice of the set of allowed operations, right? So it's somehow, the definition is relative to all of these choices. And moreover, I want to highlight that the idea of this reference is related to the concept of a reference frame, but it doesn't play exactly the same role as a reference frame. And so what we're proposing here will also turn out to be a bit different from the quantum reference frame approaches, but there are definitely connections that would be very interesting to discuss and continue exploring. And as I said, an example would be, for instance, when a clock reads some time t, Alice applies a unitary UA at the time t on the photon. So this would be an example of a conditioned operation of this type. Okay. So I should warn you, this slide might look a little bit heavy, but we don't need all of the details. But this is just to show how we can still define localization now relative to this reference degree of freedom, even if we don't have a background spacetime. And the intuition is given by this example. Like imagine now that we are considering Alice who performs an operation on a photon, and we know that it's actually localized within some time interval delta t. Then in that case, whether we measure the clock and observe that the time interval is indeed delta t, or we don't measure it, we don't expect that this measurement will disturb the photon in any way, if it were already localized in that time interval. So that's the idea of this definition. As I said, we don't need the full details, but essentially these are precisely the measurements. So we're saying that we perform these measurements and get the outcome lambda, right? So if an event is localized at the location lambda relative to the reference degree of freedom, then it will indeed have this property that measuring the reference to get the outcome lambda would not disturb the scenario. And here we also allow to have some environment that could be correlated with the reference and target through some initial conditions. Okay. And a related concept is this idea of relative measurability. And here one key difference is, if you see in localization, we are measuring and conditioning on the outcome lambda to say that, say, it's localized at some time t or at the location lambda. With relative measurability, we're just asking, just the fact of measuring the reference, does it change anything about the target? We are not conditioning on an outcome, so you would really think of this as, for instance, summing over all the lambda, right? So whether or not measuring the reference disturbs the target. And indeed, an example would be, for instance, if the reference and target are entangled in the basis of the measurement, this would not be the case, then measuring the reference would disturb the target. So that would be an example where things are not relatively measurable, as we will see in an example soon. Okay, so I can skip over these parts a bit quickly because Nelson gave a nice review of the quantum switch. But as we saw, the quantum switch is a sort of abstract process. It can be modeled in this process matrix framework, or what equivalently the framework of supermaps. And it's associated with indefinite causal order because in this representation, it implements a controlled superposition of the two orders of Alice and Bob's operations, right? And this is a purely information theoretic notion. In this talk, we will call this the coarse-grained quantum switch. Okay. So we've also seen, I guess we saw more of what's on the right side. This is the gravitational switch from the original proposal in the paper by Magdalena Zik and co-authors in 2019. And on the other hand, there are also a large class of sophisticated experiments in Minkowski spacetime, which have a claim to implement precisely this quantum switch process. And the spacetime diagram of those looks like what I've shown here, right? And on this side, what we have is sort of a superposition of these two spacetime configurations. And there has been a long-standing debate, as well as many open questions in the community on what does it mean to genuinely implement ICO, which of these do, and what are the events, what are the causal relata, and are there any differences between this classical and the quantum spacetime realizations? And there's been a lot of nice discussion I covered and across these different references. Yes, so one thing that I would want to mention is that in the context of the classical spacetime and classical agents, and I guess this, if we really consider a lab that uses the clock as a reference, and here we're thinking of agents who are, say, the classical agents who perform an experiment on the tabletop and using their classical references, one can have a description of the quantum switch scenario in this, what we call the fine-grained representation, which actually unravels into a definite acyclic order by considering whether Alice is acting at time 1 or time 2, and indeed, in the two different orders, she acts at the different times. Okay, and here one would kind of model the photon as well as sort of a vacuum degree of freedom that takes the other path. And yes, so now, given the quantum switch as well as the fine-grained version, and the different implementations, we can apply our definition of events and localizations to try to analyze what it says. One thing we could notice already here is that even though the individual operations here are localized in time, if we resolve the time in this way, if we consider this sort of extended operation, this would not be localized at any of these times, as we would naturally expect, right? Even though they can be broken down into the smaller pieces. Okay, so one thing we can say here is that when we compare these optical realizations and these quantum gravitational realizations, in both cases, so for instance here, if we condition on the time, Alice and Bob could perform different operations in the two branches, right? And on the other hand, in this particular quantum gravitational realization, because the acceleration, because they're not in free fall in this particular scenario, they could use the acceleration, and this could also give the same transformation. Right? However, the situation differs when we consider this relative measurability, because the clock time in this first scenario is not entangled with the quantum switch, but the acceleration in the second scenario is entangled with the control, right? The control is the relative distance between the mass and the agent's lab, and indeed the acceleration is directly a consequence of that. So the acceleration in the second case is entangled with the control, so measuring the acceleration would collapse the superposition. But in this case, looking at the time when I have this tabletop experiment in the lab would not collapse the superposition. So that's kind of captured by this relative measurability. And moreover, this fine-grained realization applies to the first case only when we use the time as a reference, but it does not apply to this second case because it's not relatively measurable. And this is related to the fact that agents can intervene independently relative to different points of the reference. So at time 1, I can intervene, and at time 2, I can separately perform a different intervention. So maybe I'll skip ahead, but what the point is that one can recover these two different pictures, the fine-grained and coarse-grained, under distinct assumptions on the labs. Okay, so even in the same experiment, choosing the labs in a different way gives you different conclusions on the causal order. And yeah, this provides a way out of the debate using, it's kind of specifying these lab assumptions. And yeah, maybe I will skip ahead here as well, but we can discuss it later. This is to do with the connection between these sort of quantum gravitational implementation, as well as classical space-time with superposition of trajectories, which we also saw in the previous talk. But indeed, the second and third scenarios behave in a similar way and distinct from the first scenario in our framework. And the second and third are related by quantum reference frame transformations as found in these previous works. Okay, so I will now very quickly go to the outlook. How much time do I have? Am I? Zero. Okay. All right, so then I'm just going to flash the conclusions. There's a lot of interesting work on the connections between these different things. And I think by connecting these two kind of different research directions, we can try to look for some non-classical phenomena at the interface of these different things. And clearly, as Natalia motivated at the beginning as well, there's interesting questions on the role of quantum agents in quantum space-time and how these things interact. So I will stop there. Sorry for going over time. Thank you. Thank you very much. Yeah.
One very quick question, Shoops.
Hello, thank you for the talk. I have 3 very short remarks about the first part, of about the Wigner's friend part.
Yes.
So, I'm not sure I understand, because it seems that you say the collapse has an influence on the prediction, if you implement the collapse or not. But in that case, you mean we don't choose, because if we were able to perform the experiment, like say we were able to perform the Wigner's friend, then either we will see that either we have to apply a collapse or not, and it's not a subjective choice, it's the experiment that decides. But, however, I don't even agree with myself when I say so, because
That's the problem. Yeah.
If you take, like, let's say the 6 main interpretation of quantum mechanics, 5 out of the 6 either have no collapse at all, or they take the collapse as not a physical process. Just typically this is the case for Copenhagen or Neo-Copenhagen. Most of the advocates believe that it is not a physical process, so it does not affect the predictions. And so last question, maybe this is the most important one. So what's your point concerning typically, let's say, the local friendliness theorem? Because you say if we add these parameters that account for the do we implement the collapse or not, then there is no logical contradictions. But so how do you react to the LF theorem? Do you think there is no contradiction, so we don't have to reject one of the hypotheses, or do you?
Yeah, so maybe I'll answer your second question first, because it might be faster. And the first question, I'm happy to, because it might be a longer answer, I can continue in the discussion. So for the LF theorem, indeed, that was an extra part that I didn't go into. And there, the nature of the theorem is quite different from the kind of logical reasoning paradoxes, right? So what we can say there is that essentially this absoluteness of events assumption, which is the one they're trying to refute in the LF theorem, right? This is something that's not assumed in our framework a priori. So what we can show is that the fact that things like the predictions depend on these Heisenberg cuts has a direct connection with this absence of absoluteness of events. And the scenarios where we have this, what we call setting independence, where predictions are independent of the Heisenberg cuts, we would also have a model where absoluteness of events is satisfied. So the short answer would be that we can model the LF scenario also in this framework, and the kind of assumption we are giving up to get out of the no-go theorem is precisely the absoluteness of events. So we're relaxing that to give a framework. So indeed, in that sense, because it's not phrased as a paradox, it's more a no-go theorem, so you have to give up an assumption. But for the other question on interpretations, it's very interesting, but maybe we can come back to it in the discussion, given that maybe we're out of time. Yeah, thank you.
Thank you, Vilasini.